We will have here some examples on mesh and nodal analysis. Let us now solve the problem. Find or determine Ix in the circuit shown. And to do that, I'm going to use first mesh analysis. Now, using mesh analysis, I will assign mesh currents I1 and I2, one for each mesh, and I chose or selected clockwise direction. And so, with that, by inspection, I can now obtain the equation from mesh 1, which is summation of voltage sources in mesh 1, that is 9, equal to, we are in mesh 1, so the sum of resistances in mesh 1 is 3, multiplied by the mesh current in mesh 1. And since there is a common resistance between meshes 1 and 2, I will subtract the product of the common resistance between meshes 1 and 2 multiplied by the mesh current in the adjacent mesh, meaning adjacent to mesh 1, and that is I2. So that gives me the equation in mesh 1. I now go to mesh 2. Once more, by inspection, the voltage source in mesh 2 is 6 volts in the clockwise direction. That is a negative, so we have negative 6. This is now equal to, since we are in mesh 2, your I2 will be multiplied by the sum of resistances in mesh 2, and that is 6. Then we have 6I2. Since there is a common resistance between meshes 1 and 2, we subtract product of the common resistance and the mesh current in the adjacent mesh. So there, we now have two equations, equations 1 and 2. So if we use Kramer's rule, we will be able to solve for mesh currents I1 and I2. So I1 here would be equivalent to 3 amperes, while I2 will be equal to 0. That being the case, we can now find Ix. Ix, as you see in the figure, is the current through 2 ohms, and it is downward. Therefore, Ix is equal to I1 minus I2. Substituting, we can have Ix now, and that is 3 amperes. Next, I'm going to solve also using nodal analysis or node analysis. In doing that, I need to count the nodes. We actually have 4 nodes in the given circuit. First, I will select the reference node, and I'm selecting the bottom node. And once more, since we have 4 nodes, we will be left with 3 non-reference nodes, and on them I will assign the node voltages V1, V2, and V3. Take note that between nodes 1 and the reference and nodes 3 and the reference, you have voltage sources. Therefore, we can write V1 to be 9 and V2 to be, rather V3, that's the voltage at node 3, to be 6. So given these 2 node voltages, we only have V2 as the unknown. Now, to solve for that, we are going to formulate a KVL equation at node 2, or we also call it the node equation. And so by inspection, we get at node 2 the following equation. First, there is no current source at node 2, therefore summation of current sources is 0, equal to, we are at node 2, so V2 is positive in my equation, multiplied by the sum of admittances at node 2, which are, multiplied by the sum of conductances at node 2. And those conductances are 1 over 1, 1 over 2, and 1 over 4. And you inspect, you can see that there is a common conductance between nodes 2 and 1. So we subtract the product of the common conductance, which is 1 over 1, multiplied by node voltage V1. At the same time, there is a common conductance between nodes 2 and 3. So we subtract the product of the common conductance by node voltage V3. So that completes the equation. And in simplifying this equation, we can actually multiply the entire equation by 4, giving us 0 is equivalent to negative 4V1 plus 7V2 minus V3. Then we substitute the values of V1 and V3, and that will allow us to solve for V2. So solving our V2 would be equal to 6 volts. Now, knowing V2, we are ready to determine Ix. Ix is equal to voltage across 2 ohms, which is V2, divided by 2 ohms. Now, take note the polarity of V2 is positive at the top, negative at the reference. Therefore, Ix is negative of the value, Ix is equal to positive of V2, which is 6 over 2, and that is 3 amperes. Okay, in this example, we will apply mesh analysis. We are asked here to determine Vx, and Vx is the voltage across 5 ohms. Again, using mesh analysis, I will assign clockwise mesh currents. I will call them I1, I2, and I3. Looking at I1, or rather mesh 1, we formulate the equation, and by inspection, we have no voltage source in mesh 1, so 0 is equal to sum of resistances in mesh 1, that is 10, multiplied by I1 minus common resistance between meshes 1 and 2, which is 1, multiplied by mesh current in mesh 2, which is I2. Also, there's common resistance between meshes 1 and 3. So we multiply the common resistance 4 by I3 and subtract it from the equation. Next, we go to mesh 2. At mesh 2, there is a voltage source, which is 10. And we have positive 10 because we're using clockwise, and 10 is a voltage rise. We are now at the right side of the equation where we have again common resistance between meshes 1 and 2 is 1 ohm, so we have negative 1 times I1. We are at mesh 2, so we multiply I2 by the sum of resistances in mesh 2, and that is 2 plus 1 or 3 times I2. Then we subtract common resistance, which is 2 multiplied by I3. We are now in mesh 3. In mesh 3, there is a current source, and that means we can equate I3 with the value of that current source. And I3 is now equal to negative 1. It's negative because I3 will be opposite the direction of 1 ampere. Having the following equations, we can now substitute I1, or rather I3, in the equations obtained for meshes 1 and 2. So we substitute I3 in equations 1 and 2. That way, using Kramer's rule, we should be able to get I1. And I1 will be equal to negative 0.1379 ampere. We need I1 because we are to solve for Vx, and Vx is voltage across 5 ohms. The current through 5 ohms is I1. Once more, Vx is equal to, by Ohm's law, 5 times I1. Substituting I1, our Vx would be equal to negative 0.69 volts. So there is your answer for the unknown. Before we go to the next example, let us discuss nodal analysis with voltage sources, and we will consider two cases. Here we have case 1. If a voltage source is connected between the reference node and a non-reference node, we simply set the voltage at the non-reference node equal to the voltage of the voltage source. So let us look at the figure below, and you can see here that your 10-volt source, which is connected between nodes 1 and the reference node, can be set equal to the value of the non-reference node voltage, or the value of V1. Once more, by inspection, V1 is equal to 10 volts because 10 volts is located between your non-reference node 1 and the reference node. Take note that node voltage is defined as the voltage between the non-reference node and the reference node, with the negative polarity always at the reference node, which means we can say that V1 is equal to 10 volts. Thus, our analysis is somewhat simplified by this knowledge of the voltage at this node, because it will reduce the number of unknowns. In the example shown, you have 3 unknowns, V1, V2, and V3. So with 10 volts between nodes 1 and the reference node, we can say that V1 is already given or known, and once more it is equal to 10 volts. For case 2, if the voltage source, dependent or independent, is connected between two non-reference nodes, the two non-reference nodes form a generalized node or a supernode. A supernode may be regarded as a closed surface enclosing the voltage source and its two nodes. If you look at the figure below, you have a 5-volt source between non-reference nodes 2 and 3, and therefore a supernode will be formed. A supernode is formed by enclosing a dependent or independent voltage source connected between two non-reference nodes and any elements connected in parallel with it. In short, going back, if there is a voltage source between two non-reference nodes, the two non-reference nodes along with the voltage source will form the supernode, meaning it will be treated as the same node in formulating the node equation. You will find this in the example that will follow. Here we are asked to determine Vx in the circuit shown, and Let us solve this problem using nodal analysis. By nodal analysis, we identify that we have 4 nodes, and I'm gonna select the bottom node as the reference node. With that, I'm gonna have node voltages V1, V2, and V3. From this circuit, we can now apply nodal analysis, and at node 1, you can see that there is a voltage source. Therefore, we can say V1 is equal to 5 volts. Next, we go to node 2. You will notice that between nodes 2 and 3, there is a voltage source. So that would mean we will use the concept of supernode, meaning at nodes 2 and 3, since there is a voltage source between them, we will have a supernode, meaning we will combine nodes 2 and 3 and treat it as one node. And so at the supernode, we apply the KCL. And by inspection, this will be the equation. There is no current source in or connected to the supernode, so we have 0. And this is equal now to, first, there is common conductance between the supernode and node 1. So we have to subtract the product of V1 and the sum of the common conductances, which are 1 over 2k and 1 over 1k. Now, we are going to add to this V2 times sum of the conductances connected to node 2, and that is 1 over 1k and the other 1 over 1k. Also, V3 will appear positive in the equation, again because it is part of the supernode. So we'll have V3 multiplied by the conductances connected to node 3, which are 1 over 1.5k and 1 over 2k. So this is now the equation, and to simplify this or to reduce this, let me multiply by 6k so that we can have 0 is equal to 9, rather negative 9 V1 plus 12 V2 plus 7 V3. If we substitute V1 here, which is our 5 volts, we are going to obtain the following equation, and that is 45 is equal to 12 V2 plus 7 V3. Let us call this equation number 1. Let's move on. We now go to, or rather, we need one more equation. And for the next equation, let us look at the dependent voltage source 500I, which is between nodes 2 and 3. We can therefore write the value of that voltage source, which is 500I, in terms of V2 and V3. And based on the polarity of the dependent source, this will be equal to V2 minus V3. And of course, we substitute the value of I, where I is the current through 1 kilo ohm, located between nodes 2 and the reference node. So I can be written as V2 over 1k. Substituting, we have 500 times V2 over 1k is equivalent to V2 minus V3. Simplifying the equation, we can now write V2 is equal to 2V3. Let us call that our equation number 2. We now have two equations and two unknowns. That is equations 2 and 1, and we have unknowns V2 and V3. What we need to solve is Vx. Now take a look at this part of the equation, and you can see here that Vx is actually equivalent to V3. So we need to solve for V3. And solving for V3 using equations 1 and 2, our V3 will be equivalent to 1.4516. And therefore, this is also equal to Vx. So by nodal analysis, we were able to solve for Vx, and that is 1.4516 volts.